Here we have an example of Kirchhoff's voltage law. So here's the circuit, and we're going to analyse this circuit. Let's pick some loops, or let's just find some loops. Here's a potential loop that we can analyse. Here's another loop we could analyse, and another loop we can analyse. Slightly more complicated loop that we could analyse, and there's another loop. There are more loops that we could check, but under Kirchhoff's voltage law, what we're looking for is that the sum of the voltages around any loop come to zero. So I'm going to look at the top loop and the middle bottom loop first. The reason I'm doing this is because both the top loop and the middle bottom loop are simple. There's a single voltage supply and a single resistor. So if we look at the top loop, we see that there's a 20 ohm resistor connected directly across a 15 volt supply. Now I've drawn an arrow for the 15 volt supply, and the arrow is with the head in the positive end, and I've put a positive sign on the 20 ohm resistor because that end of the resistor, the left hand end, is directly connected to the positive end of the power supply. So it's the positive end of the resistor. And if we draw an arrow there with the head at the positive end, then as we see in the equation down the bottom, 15 volts minus 15 volts equals 0. The voltage across the 20 ohm resistor has to be 15 volts because it's connected directly across the 15 volt supply. So we know that the voltage across the 20 ohm resistor is 15 volts. If we look at the middle loop, and I draw an arrow in on the 23 volt supply, and I put the positive sign on the 40 ohm resistor, and the top of the 40 ohm resistor is directly connected to the positive side of the 23 volt supply. So that has to be the positive side. So if we put an arrow on there we have that voltage, and it doesn't matter which way we go around that loop, but it's those two arrows oppose each other if we go around the loop. So 23 minus 23 is 0. So the voltage across the 40 ohm resistor has to be 23 volts because it's connected directly across the 23 volt supply. Let's have a look at the two end loops. Now both of these loops are slightly more complicated. On the left hand end we have two resistors and a voltage supply. On the right hand end we have two voltage supplies and a resistor. Now one of the loops we didn't show before was the loop that involves this 18 ohm resistor. If we look here, we've got a voltage supply, and a loop down here through the 18 ohm resistor. And if we look at the loop that's marked in, 23 volts, 15 volts, 10 ohms, the voltage across the 18 ohm and the voltage across the 10 ohm have to be the same because they share the same endpoints. This resistor is directly connected across the 23 and the 15. This resistor is directly connected across the 23 and the 15. So let's look at this loop here first. Now the 40 ohm resistor has 23 volts because we discovered that previously. So we put the 23 volts in, we put the plus sign there. We've marked in the arrow on the 5 volts. Now I'm going to start at the 23 volt because that's the largest voltage. So instead of following the direction of the loop, I'm going in the counterclockwise direction, the opposite direction. 23 minus 5 minus the unknown voltage is 0. So 23 volts minus 5 volts minus an unknown voltage is 0. If I rearrange that, I have 23 volts minus 5 volts equals the unknown voltage. Therefore the unknown voltage is 18 volts. This resistor here has 18 volts across it in the direction shown. At this end, we note that the two voltage supplies oppose each other. The positives are connected together. So going in the direction of the loop that's shown, we have 23 volts minus 15 because it's pointing in the opposite direction, minus the voltage across the 10 ohm equals 0. 23 minus 15 minus the unknown voltage equals 0. Therefore 23 volts minus 15 volts equals the unknown voltage, and the unknown voltage is 8 volts. So there's 8 volts in the direction of the arrow shown on the 10 ohm resistor, and a similar voltage, the same voltage on the 18 ohm resistor. Let's mark in all of those resistor voltages that we found, and let's try and find a slightly more complicated loop to analyse. So here's a loop we're going to analyse, and if we start the analysis down on the 40 ohm resistor, which has 23 volts across it, and we work our way up to the 20 ohm resistor and the 18 ohm resistor, we have 23 volts minus 15 volts minus 8 volts is 0. So if you follow the loop, 23 volt arrow goes with the loop, the 15 volt arrow goes against the loop, the 8 volt arrow goes against the loop. Let's have a look at another circuit. Now note, there's no arrow shown on the 23 volt, but we know that the 23 volt, the arrow points up, which is in the direction of the loop, and we know in the 5 volt supply in the bottom left, the arrow points left, which is also in the direction of the loop. So if we work our way around, I'm going to start at the 18 volts on the left hand edge. 18 volts minus 15 volts, we're going clockwise, minus 8 volts, plus 23 volts, minus 23 volts, plus 5 volts, and we're back to where we started, equals 0 volts. 18 volts minus 15 volts is 3. 3 volts minus 8 volts is minus 5. The plus and minus 23 volts cancel, so minus 5 volts plus 5 volts is 0 volts. So that's Kirchhoff's voltage law. The sum of the voltages around a closed loop must equal 0.